The topic of the video is data centers and water management, leveraging third-party data centers for water quality, treatment, desalination, real-time analytics, and intelligent water management. Water is one of humanity's most critical resources. Rapid population growth, urbanization, climate change, industrialization, pollution, and increasing water scarcity are placing unprecedented pressure on global water resources. Water utilities, governments, industries, agricultural sectors, and communities are increasingly seeking innovative digital solutions to improve water security, water quality, operational efficiency, sustainability, and resilience. Simultaneously, advances in cloud computing, artificial intelligence, AI, Internet of Things, IoT, digital twins, big data analytics, and high-performance computing, HPC, are transforming the water industry. Third-party data centers are emerging as a key enabling infrastructure for digital water systems by providing scalable computational resources, data storage, real-time analytics, and intelligent decision support capabilities. Modern water management systems are increasingly becoming cyber-physical systems that integrate sensors, communication networks, cloud data centers, AI algorithms, and optimization technologies to support intelligent and autonomous water operations. This article discusses how third-party data centers can support water management, water quality monitoring, treatment systems, desalination processes, real-time analysis, and strategic business development opportunities. The growing need for digital water management. Global water systems face numerous challenges: water scarcity, droughts, flooding, aging infrastructure, water contamination, energy-intensive treatment processes, climate variability, population growth, increasing operational costs, cybersecurity threats. Conventional water management approaches often rely on periodic measurements and manual decision-making. Modern water systems require continuous monitoring, real-time decision-making, predictive analytics, optimization, automation, risk management, intelligent control systems. These requirements generate enormous quantities of data that necessitate advanced computational infrastructures. What role do third-party data centers play? Third-party data centers provide cloud computing infrastructure, high-performance computing, HPC, big data storage, AI platforms, data analytics services, disaster recovery services, secure communication platforms. A cloud-based architecture typically follows. Water infrastructure: right-pointing arrow sensors, right-pointing arrow communication networks, right-pointing arrow third-party data center, right-pointing arrow analytics, and AI, right-pointing arrow decision support, right-pointing arrow operational actions. Third-party data centers eliminate the need for utilities and organizations to build expensive in-house computing facilities. Data sources in modern water management. Digital water systems continuously collect data from multiple sources. Smart water networks, IoT sensors, flow sensors, pressure sensors, water level sensors, turbidity sensors, pH sensors, conductivity sensors, chlorine sensors, dissolved oxygen sensors, temperature sensors, remote sensing, satellite imagery, drone observations, aerial surveys, weather systems, rainfall measurements, temperature forecasts, evaporation estimates. Infrastructure systems, SCADA systems, pump stations, reservoirs, treatment plants. Consumer systems, smart water meters, customer consumption data. These systems may generate terabytes of information every day. Cloud-based computation for water management. Third-party data centers provide substantial computational capabilities. Applications include hydraulic modeling, simulation software, EPANET, Water Gems, Mic+, InfoWorks WS Pro applications, water distribution analysis, pressure management, leakage analysis, pipe network optimization. Hydraulic models solve equations such as continuity equation, momentum equation, St. Venant equations govern unsteady pipe and open channel flows. Large urban water systems may contain hundreds of thousands of pipes, millions of demand nodes. Cloud HPC resources dramatically reduce computational times. Water quality modeling. Water quality modeling is computationally intensive. Typical analyses include contaminant transport, chlorine decay, sediment transport, nutrient cycling, algae growth, pathogen movement. Water quality models solve transport equations such as an advection dispersion equation. Cloud data centers enable large-scale simulations, multiple scenario analysis, real-time contamination tracking. Data centers and water treatment plants. Water treatment plants increasingly utilize digital technologies. Treatment processes include coagulation, flocculation, sedimentation, filtration, disinfection, membrane treatment. Data centers support process optimization. AI algorithms optimize chemical dosing, energy usage, filter operation, pump scheduling. Benefits: reduced chemical consumption, lower energy costs, improved water quality. Predictive maintenance: machine learning predicts failures in pumps, valves, membranes, sensors, motors. Predictive maintenance significantly reduces downtime. Applications in desalination systems. Desalination plants are highly energy-intensive facilities. Major technologies include reverse osmosis (RO), multi-stage flash distillation, multi-effect distillation. Third-party data centers support membrane performance analysis. Cloud analytics predict membrane fouling, scaling, biofouling, membrane degradation. Process optimization. AI optimizes pressure settings, recovery ratios, energy consumption, chemical cleaning schedules. Computational fluid dynamics (CFD) simulations analyze flow distribution, membrane module performance, concentration polarization, mixing behavior. Large CFD desalination simulations require HPC resources. Cloud computing significantly reduces processing times. Real-time water quality monitoring. Modern utilities increasingly require real-time situational awareness. Architecture: sensors, right-pointing arrow, edge devices, right-pointing arrow, cloud data center, right-pointing arrow, analytics, right-pointing arrow, operators. Continuous monitoring enables early contamination detection, leak identification, pipe burst detection, illegal discharge detection, water theft detection. Examples: if a sudden increase in turbidity occurs, 1. Sensors detect abnormal values. 2. Data are transmitted to cloud systems. 3. AI models assess severity. 4. Operators receive alerts. 5. Automated responses may isolate affected zones. Real-time decision-making significantly improves public health protection. Digital twins for water systems. Digital twins are virtual representations of physical systems. Components: physical system plus sensors plus cloud data center plus AI plus simulation models. Applications include water distribution networks, continuous simulation, pressure, flow, water quality, wastewater treatment plants, real-time optimization of treatment operations. Reservoir management prediction, water availability, drought risks, flood risks. Digital twins provide continuous monitoring, scenario testing, predictive management, improved resilience. Artificial intelligence and AI agents. AI is transforming digital water management. Applications include demand forecasting. Machine learning predicts daily demand, seasonal demand, peak demand. Algorithms, neural networks, random forests, deep learning, long short-term memory networks. Leakage detection. AI identifies hidden leaks, pipe failures, abnormal usage patterns. Water quality prediction. AI predicts turbidity, chlorine residuals, algal blooms. AI agents. Autonomous AI agents may continuously monitor systems, trigger optimization models, schedule maintenance, generate reports, coordinate emergency responses. High-performance computing requirements. Large-scale water simulations require significant resources. Examples: simulation type. Typical requirements: national water model, hundreds of CPU cores. CFD treatment simulation, thousands of cores. Flood simulation, GPU clusters. Digital twin platform, continuous cloud resources. A national-scale hydrological model may generate petabytes of data annually. Cloud HPC offers elastic and scalable resources. Cybersecurity and data security. Water infrastructure is critical national infrastructure. Cybersecurity is therefore essential. Major risks: ransomware attacks, data theft, infrastructure sabotage, remote control system compromise, insider threats. Recent cyber incidents globally demonstrate increasing risks to water utilities. Security measures: encryption, AES 256, TLS communication, zero trust security, continuous verification of users and devices. Multi-factor authentication, additional authentication layers. Role-based access control restricts access privileges. Network segmentation separates operational technologies from business networks. Security monitoring, continuous intrusion detection systems. Post-quantum cybersecurity. Future systems should increasingly adopt post-quantum cryptography, quantum-safe communication, quantum key distribution. Costs of third-party data center usage. Traditional in-house infrastructure may cost Item approximate cost HPC cluster AUD 1 to 15 million storage systems 500,000 Australian dollars plus data center facilities AUD millions IT personnel significant ongoing cost cloud-based services usually involve compute charges AUD 0.10 to 20 per CPU hour GPU charges AUD 2 to 50 per GPU hour storage charges AUD 20 to 100 per terabyte per month data transfer charges variable depending on usage. Pay-as-you-go pricing significantly reduces capital expenditure. Business benefits. Third-party data centers provide substantial business advantages. Reduced capital investment, no need to build local data centers. Scalability, resources increase on demand. Improved operational efficiency, optimized water operations reduce costs. Better asset management, predictive maintenance extends asset life. Enhanced sustainability, reduced energy and chemical consumption. Improved customer service, faster incident response. Increased resilience, better preparedness for droughts, floods, and emergencies. Faster innovation, utilities can rapidly adopt emerging technologies. Real-life applications, smart cities, integrated urban water management platforms. Large water utilities, real-time optimization of distribution networks. Desalination plants, cloud-based membrane optimization. Agricultural irrigation, precision irrigation using cloud analytics. River basin management, integrated watershed modeling. Flood forecasting, cloud HPC supports real-time flood prediction systems. Emerging technologies and future directions. Future water systems will increasingly integrate AI agents, quantum computing, quantum machine learning, digital twins, edge computing, blockchain, robotics, autonomous drones, satellite analytics, 6G communications. Quantum computing may eventually transform water network optimization, desalination design, chemical process optimization, large-scale hydrological simulations. AI agents may autonomously manage entire water infrastructures. Consultancy, collaboration, and business opportunities. Significant opportunities exist for water utilities, digital transformation projects. Consulting firms, smart water consulting services. Universities, collaborative research and training. Technology companies, cloud platforms and AI solutions. Startups, innovative water analytics products. Government agencies, smart water infrastructure programs. Potential activities include consultancy projects, research grants, professional training, industry partnerships, joint publications, pilot implementations. Conclusion. Third-party data centers are transforming the global water sector by enabling advanced computation, real-time analytics, intelligent decision-making, and scalable digital infrastructure. Through the integration of cloud computing, AI, digital twins, IoT, HPC, and emerging technologies, water utilities and organizations can improve water quality, optimize treatment and desalination processes, reduce operational costs, enhance sustainability, and strengthen resilience. The future of water management will be increasingly digital, intelligent, autonomous, and cloud-enabled. Organizations that strategically adopt these technologies will gain significant competitive, operational, environmental, and societal advantages while contributing to global water security and sustainable development. If you enjoyed this discussion, don't forget to subscribe, like, and share. Stay tuned for more insights on AI, quantum computing, and emerging technologies shaping the future of software and humanity.